All right, so we are now in chapter 2. Chapter 2 has two parts. One is logic, that's in section 1. And then, logic, and then sets. And sets has two parts to it, basics about sets, and then set operations. And it's going to take us a week and a half to go through this, and at the end of next week, we're going to have our first exam on chapters 1 and 2. So mostly what we're going to do in logic here is deductive reasoning. Back in chapter 1, when we were playing with patterns, there was a section in there called inductive reasoning, which we've already looked at. Deductive reasoning is taking some general information and getting specific conclusions. And so this is the main goal for this section. To understand that part of logic. All right, so warming up to that goal, a big thing in logic are just statements. And a statement is essentially a simple sentence. It could be something like 2 is an even number. It could be something like x plus 2 equals 5. Or more complicated, which is kind of part of our goal here. If a number is even, then it is divisible by 2. Back up there. Some statements we can do things like negate them. That's a big topic in the beginning. So again, the last one is if a number is even, then it is divisible by 2. And I can negate each of these. Except maybe the first one. So that's too simple. Like x plus 2 is not equal 5. Instead of a number is even, a number is not even. That more complicated one, if a number is even, then it is divisible by 2. Negating that would be if a number is not even, then it is not divisible by 2. So for many things, a negation is just putting a not in front of whatever the verb was, or whatever the focus was, like equal versus not equal. even versus not even, divisible versus not divisible. But sometimes it's not as obvious depending on quantifiers that are listed. So we'll go over quantifiers and then how they're related to negation. Quantifiers are things like all, every, each, or maybe none. And all, every, each, these are synonymous. We might also see, instead of all or none, those are two extremes. In the middle would be some. Right? They denote a quantity, but the sum is a little vague. Like, what is sum? All, that's clear. Everything, right? None, nothing. Some, somewhere in between. There's a lot in between nothing and everything. That gets a little harder. Sometimes instead of some, it might be there exists at least one. So what does sum mean in math? It means there exists at least one. Could be more than one, could be only one. Could be a million, could be infinitely many. All right, negation and quantifiers. How do we negate these? So something like all A's are B's. Could be something like all even numbers are divisible by 2 was a statement I made earlier. A and B could be any kind of simple statement. Negation of that. Some A's are B's. And you've done simple negations in other ways. Like a negation is kind of like the opposite. Right? Equal versus not equal. Those are opposite things. -1 versus +1, opposite things. So what's the opposite of 1? Opposite of 1. What is it? -1. What's the opposite of -1? 1. They go back and forth. So it says, so if you started with some A's or B's, what would the opposite or the negation of that be? All A's or B's. Yeah, if you negate the negation, you get back to where you started. Kind of like the opposite of -1 is 1. Same idea. No A's are B's. Negation. Some A's are B's. So what would the negation of some A's or B's be? No A's or B's. Yeah, it goes back and forth like that. Okay. But the most common misconception in logic is that the negation of all A's or B's should be no A's or B's, but that's not true. So all I need to prove something is not true, like a negation, is one counterexample, and that's where sum comes in. Okay. So if something is not true in general, that means there's at least one instance where it doesn't work. And that's where this comes from. So we're just doing a crash course in logic, then we'll look at some specific problems using these things. So that was the first part. Next part is the idea of truth tables. Oops. So truth tables are ways we take these logical connections of things and explain how they work together. So the things we're going to work on in truth tables are negations, conjunctions, conditions. So we've already looked at the idea of what a negation is. It just means say the opposite. Usually the opposite is using not, the word not. But every once in a while we have to negate all, which is some. Or we have to negate no, which is some, which is a weird thing you have to get used to. So I'll show you what that looks like in a truth table in a minute. A conjunction, do you remember, ever guys Schoolhouse Rock? I don't know if anyone's ever seen that, where they sang songs like conjunction, junction, what's your function? You guys are too young for that. Damn, I gotta play you that someday. So a conjunction is a way we connect things. And common ways we connect things are and or are the most common ways to do it. And those are the ones we're gonna look at. So one conjunction is an and the other one is an or. And then conditions are if, then is the condition that we're going to look at. And so we need to figure out how these work together, separately, negations. So we're going to mix them all up and define truth tables for that. All right, so think about and for a second. In common language, you might get things like you can have ice cream or cake. So if my mom said that to me, I was like, oh, fine, I got to pick one. But in math, an or really means and or. You can have ice cream, you can have cake, you can have both. So that's something you kind of get used to here. So in math, this is called an inclusive or. Versus in regular language, like when my mom's talking to me, it's an exclusive or. You can't have both. So that's a new thing to get rid of, to get used to here, that idea of an inclusive or. So if I was going to make a truth table for the conjunction or, it would look like this. We have something we call P. Could be ice cream. Could be, did you do your homework? Could be, is this an even number? It's some simple statement or thing. Q is some other statement. Could be cake. Could be being an odd number. Could be being a prime number. Any simple thing or simple statement. And what we want to do is, based on the truth of P and Q, what might be true for P or Q? We're going to make a truth table for that right now. So let's say it's true you get ice cream. And it's true that you get cake. Is it true that you got ice cream or cake? Yeah, definitely true. True for P. False for Q. And again, it might not be ice cream or cake. It could be something like, even number or prime number. True, you get ice cream. False, you get cake. What about getting ice cream or cake? Is that true or false here? Turns out it's true. As long as one of them happens with an or, the or is happy about it. So it turns out that has to be true. Now, there's nothing special about the order of these. I could have said cake or ice cream. So that means if I go false and then true, this still ought to be true. So the only time an or is going to be false if they're both false. Oops, that's not very good. F. This looks like a T. So if I was doing the even or prime number, and I picked a number like 2 as my number to test this out. Is 2 even? No. Is 2 prime? No. So for or, 2 would be this first line here. Is 2 even or prime? Yep, it is even or prime. If I switch the number to, say, 4, then that jumps me to the second line here. Is 4 even? True. Is 4 prime? No, it's not prime. But if I asked, is 4 even or prime, we would have to say yes. It is even or prime because it fits the even part. If I switch to the number 3, that would be this line here because 3 is not even, but it is prime. So that means it is even or prime, mathematically speaking, because we're using this idea of an inclusive or. If I picked 9 as the number I wanted to test, 9's not even, 9's not prime. So is 9 even or prime? The answer is no, that's false. It's not even or prime. Right? So then that would be like this line down here. And it doesn't matter whether I'm talking about cake or ice cream, even or prime, or any other things you try to connect with or. This is always the structure of how P or Q is related to P and Q individually. So the truth table tries to whittle it down. For any things we try to connect with or, what's the end truth or falseness based on what we know about each one? And the cool thing about logic is, doesn't matter what P and Q are, this is the way it always has to flow. And so that is the truth table for an or statement. And let's see, we have another name for or, which is a disjunction. Should add that to our notes. Or is also called a disjunction. And then sometimes you'll see it written like this. So that just means, again, P or Q. So sometimes in a homework problem will come up, or an example in the book, they'll use the word or. Sometimes they'll put that V symbol in between. That also means or. Sometimes they'll use the word disjunction. That means or too. Object. Page. Truth table for an and. So P, Q, P and Q. And again, we could be talking about cake and ice cream. We could talk about evens and primes. There's lots of different things we could talk about with that. So I'm just going to go back to the cake and ice cream part. So if I had cake, I had ice cream. Did I have cake and ice cream? The answer is, well, yeah, cake and ice cream. Pretty straightforward. If I had cake, but I didn't have ice cream, did I have cake and ice cream? No, that would have to be false. So if I don't have any one of them, the and says it's false. It's only one time where and is true. that is the truth table for an AND. Sometimes AND will be written with that symbol. Here's the hardest one individually, and then we'll start trying to put them together. Conditionals. Conditions. Sometimes we write if P, then Q, or you might see P arrow Q. Sometimes it's written P double arrow Q, but the arrow has a direction. That direction is very important. Order they're stated matters. And I'll give you an example of it. If you finish your math assignment, then you can have chocolate. I like chocolate. I have a nice bar of chocolate at home, but I can't have it tonight until I finish grading all my math stuff. So that's my motivation. Does that guarantee I'm going to finish my math assignments? No. Might I have the chocolate anyway? Maybe. Might I finish them but not get to my chocolate? That's possible too. Might I have neither? That could happen too. There's lots of things that could happen here. So you finish your math assignment, that's my P, and you can have chocolate, that's my Q here. So we're going to come up with a truth table for this. P, Q, if P, then Q. And to do this, the thing I need to share with you to make it make sense is a condition. A conditional is a promise. And the promise is only false if it is broken. Otherwise, if it's not broken, it's true. It doesn't violate any laws of logic. So it could be that I finish all my math homework, all my math assignments. Could be that I get chocolate. Well, if I finish my math assignments and I got the chocolate, then this promise happened just the way it was supposed to. So it is true. Suppose I finish all my math assignments, but I don't get chocolate. The promise is broken. That's the only time it's false. Now, the promise here is if you finish your math assignment, then you can have chocolate. That's it. Okay. Are there other reasons one might have chocolate? Sure, this is just one of them. So if I don't finish my homework, but I do have chocolate, the promise is not broken here. Right? I'm not obligated to give myself or anyone else chocolate if they didn't finish their assignments, but I could, it would still true. That one's the weird one. I had to let that sink in when I first learned that. I don't finish my homework. I didn't get any chocolate. Doesn't break that promise there, so it's still true. For some reason, that last one was easier for me to get than the third one. First and second make perfect sense. The other two are kind of like, really? Yeah, that's the way it goes. Thinking about it that way right there. So a condition is a promise. The only time a condition is false is if the promise is broken, and that only happens with a true and then false premise and then conclusion. Yeah.
But why is the last one true?
Because the promise is not broken. So the thing we have to think about a conditionals is you think of a condition as a promise, right? So I promise if you finish your homework, you're gonna have chocolate, right? But you didn't do your homework. You didn't get chocolate. That doesn't break this promise. And so it's still true. Yeah, so the only time it's gonna be false is if we break a conclusion. If we don't follow through with what it says, then it's false. Otherwise, it's always true. And that's the weirdest truth table. Next. Apply conditionals yet. Yeah, we're going to stick with regular conditions for now. So there's three ways we can modify a conditional. So a conditional is something like if P then Q. And we'll put another statement in there to play with that in a minute. So that's my original statement. I could do the converse of that. Switch color. And converse just means switch. So the converse would be if Q, then P. I could do an inverse on a conditional. And inverse just means negate. And instead of writing the word not, sometimes instead of say not P, you'll see a tilde P, and they mean the same thing. I like not, the book likes tilde. So I would write if not P, then not Q. In the book, they'll instead write if tilde P, then tilde Q. So the tilde in logic means a not. And then there's a very interesting one called a contrapositive. Go. And contrapositive means switch and negate. So that would be if not Q, then not P. So I'm going to give you a statement in a minute, and I want you to try and write the converse, the inverse, and the contrapositive of the conditional that I gave you. And then we'll talk about them a little bit. So we have to get the original statement. We have its converse, which is just switch the premise and the conclusion. We have the inverse, which means leave the same order, but just negate them both. And a contrapositive, which means switch them and negate. So here's the statement. if I am at Blue Mountain Community College, then I am in Oregon. So what I want you to do is, given that statement, write its converse, write its inverse, and write its contrapositive. And I'll pause for a second and then I'll write my versions of them and see if we agree.